You just talk slowly.
So, yeah.
You know, Singaporeans come 5 minutes late.
Okay, so good afternoon. So it's 12:01. Let's start this afternoon's lunchtime science series talk. Okay, and today we are very happy to have Professor Andrew Wee, who is the Provost Chair from the Department of Physics, to come and share with us on adventures in Flatland, perspectives from a surface scientist. Professor Andrew Wee requires no introductions. In fact, he has been standing at this particular position, giving many talks. Most of the time, we don't hear him talking about science. It's more about administrative matter as a former dean of Faculty of Science. So today will be a very different flavor. Prof is going to talk about his scientific research and achievement. Okay. So for the benefit of more junior members, like the students who do not know Prof Wee's education path, I would like to introduce him. Professor Andrew Wee is a Provost Chair of Physics and Vice President, University and Global Relations at the National University of Singapore. Okay. He has many accolades. He is a President and Fellow of the Singapore National Academy of Science, SNAS. Okay. He's also a Fellow of the Institute of Physics, UK Institute of Physics, Institute of Physics Singapore, okay, the former past presidents of Institute of Physics Singapore, and an academician of the Asia Pacific Academy of Materials, APAM. Okay. His research interests include scanning tunneling microscope, STM, and synchrotron radiation studies of the molecule-substrate interface, graphene, and 2D materials, and related devices, related device studies. Okay. Now, this is very important. He is an associate editor of ACS Nano. So those of you who want to submit your paper to ACS Nano, then you know who to talk to. Okay. And on the editorial board of several other journals. Okay. He holds a BA, Honours, and MA in Physics from University of Cambridge, Doctor of Philosophy from the University of Oxford. See, he went to all the right schools. Okay. and a PGCE from the University of London. Okay, so without further ado, I would like to invite Professor Andrew Wee to come and share with us his perspective on the Flatland.
Thanks. Good afternoon. First of all, I must thank you all for coming because I know there are so many things going on, and a talk like this, normally we need put some effort to come, and in particular, must thank my distinguished colleagues from other departments, mathematics and so on, who don't normally listen to talks. Statistics, right? Yes, amazing. Okay, I'm sorry, there are no equations at all. So I hope you can understand it. But I must say, yes, he's right in saying that normally I speak about administrative things here, but actually I prefer to talk about science. I have to tell you the truth. So today, at last, I get to talk a bit about science. But because it's a general audience, I see some of my current students and former students in this audience as well. So it's a very broad audience. So please bear with me if some of it is too basic. But I shall try to make it interesting in a storytelling way with a little sociological perspective. That means talking about the people involved in it as well. It will cover roughly the past 10 years of the work, but it's not exhaustive, it's just selective. You see biases in certain areas because I wanted to show more pictures. So I couldn't cover the work of all the people in our group. So just to let you know, that's the backdrop. So why did I choose the title Adventures in Flatland? Because those who are familiar, this is taken from a little novel that some of you may have heard of. It's actually a very old novel called Flatland, A Romance of Many Dimensions, written in 1884, a satirical novel by an English schoolmaster, Abbott. And it's basically about a two-dimensional world of Flatland, and it's a commentary on hierarchy of Victorian culture, but of course its more enduring contribution is its examination of dimensions. If you go to YouTube, there's even a cartoon movie made from this, and it's quite interesting. I watched it, and of course it talks about different people are different shapes, they're moving around in Flatland, but of course in the end someone comes from the third dimension and it upsets the whole the whole world. So it's interesting, that perspective. So I start there because the scope of my talk today is really to tell three stories. Okay, that's why I use a story theme. After an introduction to set the stage, I'm going to talk about our adventures with molecules, and then graphene, and then finally what we're doing currently on various 2D materials, and then make some final remarks. So by way of introduction, first of all, I have to tell you all what is surface science. For those who are not my group, I know there's some of you in my group who are surface scientists, you know this very well. But many people wonder, what is surface science? What are we doing? Are we just studying at the surface and nothing in depth?
Science.
Yeah. Oh, sorry, typo. Okay, I hope there are not too many typos. So if you look at Wikipedia, the definition of surface science is the study of physical and chemical phenomena that occur at the interface of two phases, be it solid liquid, solid gas, solid vacuum, liquid gas. And it includes the fields of surface chemistry and surface physics. So it is certainly a multidisciplinary field. I have colleagues in chemistry who we speak the same language because we work in this field. I also want to highlight that actually most surface scientists, the traditional ones like myself, work on a solid vacuum interface, especially those from a physics perspective, because we don't like liquids, it's too messy. So we just have a solid and a vacuum, and then whatever we put in between, there's nothing else to confuse matters, okay? Why is it important? Why do we want to study surface and interfaces? So I just use a quotation from a Nobel laureate at his Nobel lecture in 2000, who won a Nobel Prize on heterostructured devices, right? So he's a device physicist, but he said that often it may be said that the interface is the device. So why is that so? Why is the interface the device? In fact, all the devices you have from your mobile phone and so on, all the chips in it, really it works because of the interfaces. And why is that so? So just to set a backdrop for the motivation, I guess one of the general motivation of our work, but not the only motivation, because there are other fields that need surfaces like catalysis, corrosion, and so on. But one of the motivations of our work is the field of microelectronics, because that's very important technology today. And as an example, most of your PCs right now use the Intel 22 nanometer process. Now, what does 22 nanometer mean? That's typically the indicative size of the gate length. It's a feature in the device, the smallest feature in the device. So, for example, your i5 processor uses the Intel 22 process featuring what they call tri-gate transistor. Most of you have never taken a transistor apart. You may have seen pictures of transistors. This one is a little bit different from the normal CMOS planar transistors in that because when they make transistors smaller and smaller, you run out of space, so they start using the third dimension. So they use fins. That's why it's called FinFET. Okay? You use fins so you can increase the area of the gate, and these things stick out three-dimensionally. So now your IC chips, if you look at it, it has structures standing up in order to bring it down to 22 nanometers. Now, 22 nanometers is not a lot of atoms. If you look at it in the transmission electron microscope, a cross-section of a fin that's 22 nanometers, you can almost count the number of atoms, right? Because one atomic spacing is less than a nanometer, so there are not many atoms there. So you would imagine that the device is all interface, right? All the interface properties define the device. And this 22 nanometer, where they started research a few years ago, is currently in production. But right now, people are working at 10 nanometers and below. And we are probably reaching the end of the length scale for the type of devices that we're used to. Because if we get smaller and smaller, other effects become important, particularly tunneling effects, quantum effects, and so on. So we may have to look for a different paradigm. So for example, this iMac image shows a 6 nanometer FinFET. So 6 nanometer is just a few atoms, right? So we're probably approaching the limit for this kind of architecture, and new ideas will be needed soon. But coming back to surface science. Now, what distinguishes surface scientists? I said we work on a solid vacuum interface. So we use ultra-high vacuum. So question, why ultra-high vacuum? So all our equipment look like this. It's all stainless steel. If you enter our labs, it's all stainless steel. It all looks the same. Now, let me tell you the main reason why. Okay, ultra-high vacuum generally is 10 to the minus 9 millibars or lower. 1 bar is atmospheric pressure, so 10 to the minus millibar is 12 orders of magnitude below atmospheric. So it's like near space. It's like almost being in space inside if you can get in the chamber. Okay? So of course you wouldn't survive that because there's hardly anything inside. It's almost empty. Just to put things in perspective, at 10 to the minus 6 millibar, which is 3 orders of magnitude above this, a layer of gas atoms will form on a surface every 3 seconds on the assumption that every atom sticks to the surface. Of course, in general, every atom does not necessarily stick. There's a probability that it will stick. So the reason why we need vacuum even lower than that is because we need to do an experiment on the time scale before a layer of contaminant molecules deposits on it. In other words, the surface must remain clean or with whatever we want to put on it without any other extraneous water, oxygen, or whatever contamination on it. So that's the reason. Now 10 to the minus 9 is achievable. Normal turbo ion pumps that you have in your labs actually will reach this pressure, but most of the time you only reach 10 to the minus 6, and it will take a long time, depending on the pumping speed and pumping volume, before you reach 10 to the minus 9 or below. But a surface scientist will know, we quicken it by baking it. It's like an oven, we bake it. So why do we bake it? So typically we either cover it in foil or put it in a big case oven and then heat it to 180 degrees or higher for at least 1 day. By heating the stainless steel and everything to that temperature, you accelerate the degassing process Because where are all the molecules? They are all sticking on the walls, right? And they slowly come off the surface through time. And that's what causes all the residual pressure. But if you bake it, it all comes off more quickly. And then when you cool it down, the pressure drops. Okay, you know that because when you heat a bottle and then you close it up and cool it down, it becomes a vacuum inside. So we are accelerating the process. And now typically we can get to 10 to the minus 10, 10 to the minus 11 base pressures. And that's important because we want surfaces that are clean. So this STM image shows a surface, at least within this length scale, you can't see any other contamination on it. And then you can study single molecules on the surface and so on. So that's basically why surface scientists are so bothered. The first thing a surface scientist does is he goes and looks at the pressure gauge to make sure that the pressure is in the right regime before he even starts an experiment, okay? And the thing we don't like most are leaks, right? Sometimes you spend a long time finding a leak, and a leak that lets the pressure up even 1 atmosphere can really ruin our day because we wouldn't be able to do the experiment. So these, over the years, we have built several systems, and they all, to a layman, look the same, right? It's all stainless steel, but they have different tools on it, different techniques that come with acronyms like XPS, UPS, AES, STM, SIMS, PES, XCS, and so on and so forth. I'll talk about a few of them, and in particular, because this is a general talk, and I like to show pictures, I will emphasize the scanning tunneling microscope because it is a means of producing atomic scale images. Most of you have heard of it. It was invented in the early 80s. Binnick and Aurora, they won a Nobel Prize within 5 years of their publication, which means everyone recognized it as significant. Because it was the first time we could image atoms on the surface in real space. Of course, we could get atomic structure through diffraction and other indirect methods previously, but this is the first time we could get an image in real space. Of course, the interpretation sometimes is a little bit tricky, like on silicon, which is a semiconductor. So you have an electronic image. So you are actually looking at the electronic topography, as it were. But most of the time, it corresponds to where the atoms are. And you can do some experiments to try to disentangle the electronic and physical topography. But you imagine if you have a tip scanning the surface atomically sharp, you can not only get an image, you can do many things. You can get spectra, you can do IV curves on it, I'll show some later. But you can also use a tip as a probe to move things around, right? And this very famous image by IBM was the first time Don Agler in 1989 in IBM Almaden used an STM tip, or his student or postdoc, to move individual helium atoms on a metal surface to make the words IBM. Of course, it took many hours to do this because it takes a while to pick and push the atoms around. And it was done at 4 Kelvin, at low temperature, so that these helium atoms don't run away. Very nice for publicity purposes. We haven't yet found a use for this, right? But many people, of course, have dreams that, Feynman said in 1959, in the future, we can arrange atoms the way we want. We can do amazing things at the atomic scale, and in a sense, it is a demonstration that this dream has come true. Okay, of course, besides the STM, we have other techniques. For example, the synchrotron, we have a beamline. We do a lot of spectroscopies there. We have X-rays in this energy range. Why this energy range? Because we produce low-energy photoelectrons, and photoelectrons of a few hundred electron volts have a very low inelastic mean free path in solids. In other words, they are very surface sensitive. In other words, they only travel a short distance before being scattered, so most of what you measure comes just from the first few layers of the surface. So you would see a lot of electron spectroscopies are used by surface scientists. They are inherently surface sensitive. Even for diffraction, low energy electron diffraction gives the structure of surfaces at the top or top 2 layers. So we do a lot of this as well. But as I said, I'll focus on the STM because it shows nicer pictures. And okay, I'll say something about, of course, our field of surface science, we were very hot in the 70s, 80s, and so on. And then after a while, I guess funding agencies start funding new things. So I guess many surface scientists now tend to come under the field of nanoscience for funding purposes. But nevertheless, I also teach a course in nanoscience. Some of my students are here. Nevertheless, we do things at a nanoscale, right? Although it's two-dimensionally nano in that direction. But the field of nano is interesting because it is the first time since the 80s and 90s that physicists, chemistry, and biologists can work together because they are working on the same length scale. In fact, chemists have always worked at a nanoscale because molecules are nanometer scale. The difference is whether chemistry is nanoscience. The difference is that they tend to work with large assembly of molecules in a beaker. They don't talk about single molecules at a time until recently, mainly through the surface chemists. Biologists, of course, they work on large macromolecules, but they are starting to use them, or at least engineers are using biological molecules to make biological nanomachines, okay, inspired by biology. And of course, you saw that physicists and engineers, they try to make devices smaller and smaller until they reach the atomic and molecular scale. So there's this multidisciplinary field. So one of the themes of my talk today is to emphasize that science is multidisciplinary. It doesn't mean that just because we hit chemistry, then the physicist stops there and turns around and goes back. So we have to learn some chemistry as well. So in fact, as I'll show you later, I publish in chemistry journals as well. Yeah, I've said that point. Yeah. Okay, so this is Moore's law, where coming back to scaling of chips, you can see transistors going from vacuum tubes to transistors. So transistor hasn't changed for the last 40 years. I mean, in terms of, it's just changed in length scale, but in terms of the basic architecture, it's still the field effect transistor. But in the near future, if you want to make further progress, we are likely to have to look for a new paradigm. And that's why our colleagues here are looking at quantum computing. Some people elsewhere in the world are looking at DNA computing, optical computing, and so on and so forth. But of course, one area we are interested in is molecular electronics or molecular computing. Naturally, because we have tools to be able to probe single molecules, right? So naturally, in the 90s, our research, we had some grants working in this related area. So the idea of molecular electronics is that to make a device with a single molecule, whether that's possible, because a molecule is less than a nanometer, so that's much smaller than your 20 nanometer gate. If you could make it at that scale, you can make high density memories or devices. So that's the dream. Of course, it has not come true. It's not, or yet, it's not easy. But certainly it's an interdisciplinary field because the physicist have to learn about molecules, and the chemist needs to learn some electronics, and so on and so forth. So some of our colleagues in NUS are working in various aspects of it. The key is how you can control the properties of these single molecules, arrange them, and then control their properties in order to make switches and so on. So this is, of course, just a schematic. It's a dream, what they hope to do, but of course, in reality, it's quite impossible to make something like this. This is a real experiment, but it's a schematic showing that if you put a molecule between two electrodes, if you apply some external, in this case, I think it's a field, you can change the conformation, the shape, and then you can change the conductivity of the molecule just by realigning these two benzene rings. So that backdrop of molecular electronics leads me to my first story on the work that we really started around 10 years ago. And I'll tell you who are the key people involved in it. So we started working on molecules. Like, I'm a physicist, so prior to that, the only molecules I worked on was probably oxygen and the simple molecules that physicists are comfortable with. But then I had a great PhD student. His name is Chen Wei, whom you all know, in the early 80s. I co-supervised him with Lo Ken Ping. And it wasn't part of his PhD project because he was working on silicon carbide. I'll show you some of his work. But when he did his postdoc, when he became an LKY postdoc, I said, since you are a chemist, and this field of molecular electronics is interesting, why don't we put some interesting molecules that people are interested in using on the surface, right? So he's a chemist, he's comfortable with that. So he led the way. And there were other students and postdocs as well. And of course, the first thing we could do is, the amazing thing is that molecules like to order themselves, if possible, on the surface. Okay, well, in this case, they are not ordered, but their particular location is ordered on a particular template because there is a lowest energy position. They will rather sit. But sometimes they arrange themselves in rows, one-dimensionally. So you can think of them as molecular wires if they could conduct. Sometimes they form a whole two-dimensional plane. So you could think of them as two-dimensional heterostructure layered material. So you can see from 2007 to the next 5 years, we published a lot of papers studying molecular self-assembly because not many people worked in this field at this point in time, partly because I guess you have to, it's interdisciplinary. One lesson we learned is that people tend to avoid the space between disciplines. The physicist will do the physics, the chemist will do the chemist, and there are not so many people working in between. So by choosing an area in between, actually you find that a lot of people are interested. So in this period, it was easy to publish in this field, and we did. But of course, after a while, everyone started doing the same thing. So we moved on since. So for example, we published in a physics journal where we assembled a P and an N-type molecule on a surface. It's self-assembled. We didn't have to move them around. It wanted to arrange this position. And of course, there were some highlights in, I think this was a highlight in Nature Nanotechnology saying that, oh, you could make a bottom-up method of producing a PN rectifying junction with C60 and 6P molecules on a surface like this, because we showed various ways of assembling these two molecules. Of course, in principle, yes, we have demonstrated a molecular PN junction, but the difficult part is then connecting it up the external circuit, right? We just demonstrated it, but it's not easy to make a contact to one molecule, and there's a lot of people working, figuring out how to do that. So the physics community was interested, and of course so was the chemistry community. So this is in the chemistry journal, again looking at assembly of another molecule on the surface. So very multidisciplinary. We've published both in physics and chemistry journals during this period. This is Huang Han, someone who came a little bit later, now a professor in Central South University in China. He was a CSC scholar and then became a postdoc and then went back. Now, Yuli is another PhD student who carried on STM work, and now she's working in IMRI. So she's still around. Okay, so she was, then we could assemble things very well. Then we wanted to say, can we manipulate and do things to single molecules, okay? Create some function at the single molecule level. So here was a demonstration of using the tip, in this case, by applying a tip on this molecule is polar. That means it has a chlorine atom sticking out of it, right? So it has a dipole. So if you image it on a STM, it self-assembles in a square-like lattice with a bright spot that is the chlorine atom up. She showed that you can actually pulse it appropriately and cause a change here, okay? And actually what happens is that the chlorine goes down. So it looks like the molecule has flipped or the chlorine has gone down. And this was, of course, the first step of making the word NUS, right? This is just the N. And the demonstration was you could do it in a forward direction, and the red arrow shows that you can do it in the backward, reverse direction. So you have a reversible way of changing the conformation of a molecule. And of course, if you think about it in electronic terms, you can do binary operations on it, because a 1 is an up and a 0 is a down, right? And then you can write, and then you can read it, and the spacing between it is only one molecule. So we calculated is 25 terahertz or terabits. So you can store very much more memory than your current devices. But of course, the problem is stability. These things were done at liquid nitrogen temperatures. It's generally stable up to room temperature, but at room temperature it becomes harder to position your tip without thermal drift and so on. So the practicalities of making a device this way, there are a lot of challenges. But it was an interesting demonstration, and there are other people doing variations of this with different molecules to demonstrate high density memory, for example. Okay, well, I wouldn't talk about the mechanism. Further studies were done to study the mechanism, and we actually, in the end, concluded that it was the tunneling of the chlorine atom that causes this apparent flip. So that's the first story. what we did on molecules, but all that sort of ended 5 years ago, although we still use molecules, but we didn't focus just on the self-assembly part. I'll talk about our graphene story because we as surface scientists, we are interested in surfaces and interfaces, but we can work with any material, right? As long as it's solid, stable in a vacuum. So it turns out that graphene became a hot thing, right? And in the past, people worked on buckyballs and nanotubes, but these are not flat. So generally, while we can do some surface analysis on it, we can't really do nice STM on it. So we ignored the field. But when carbon became flat and single sheet, then it became a surface, right? And naturally, it's ideal for the tools of surface science. So that's where we came in. And those of you who know the history, actually it was these three chemists that won a Nobel Prize, first for the zero-dimensional version, which was the fullerenes, and then these two physicists from Manchester won the Nobel Prize 2010 for graphene, the two-dimensional version. The 1D version, the nanotube, Ijima didn't get a Nobel Prize. He got many awards, but he didn't get a Nobel Prize for that. And okay, that's just showing that how the publications trend moved from fullerenes to carbon nanotubes, and now graphene overtakes them all. Okay, so at 2012, well, I did an editorial in ACS Nano talking about graphene. We noticed suddenly so many people publishing in the field of graphene. And in particular, when at that point in time, in June 2012, when we did a SCI search, Singapore universities ranked pretty high just in terms of the number of SCI papers published at that point in time. Okay, profiles have changed, people have moved away from graphene and so on. But it was interesting to see the sociological effect of people moving fields. So how did we enter graphene? Actually, surface scientists have been working on graphene since the 70s. I'll say pseudo-graphene because the graphene is not isolated, it's on a surface. It's a single layer of carbon. The only problem is we tend to treat it as contamination. So we sputter it off and remove it, okay? So for example, this is part of the work that Chen Wei did in part of his PhD, where we were studying silicon carbide. We were interested in the atomic structure of a nanomesh reconstruction on the surface that looks something like this. It's actually, this mesh has an atomic spacing of 2 to 3 nanometers. It actually is the precursor to graphene formation. So you just heat it 100 degrees more, then a graphene layer forms due to more sublimation of silicon. And we actually showed the graphene as well. But of course, the paper didn't focus on that because at 2005, we didn't read about the first few graphene papers, which sort of came out in 2004. But of course, within a year or two, we realized that, why don't we work on epitaxial graphene, as this graphene is called because it's grown epitaxially on top of silicon carbide. Why don't we work on this area since we have been working on it all along, but we were doing something else with it. We were using this as templates to put molecules into the holes, which we did, fullerene molecules in holes, which was very interesting. But we switched and we focused on the graphene layer that forms on top of the nanomesh. You can see the corrugations here is the second layer of the nanomesh. On top of these corrugations, you can see all these spots on top. That is the layer of graphene, a single hexagonal lattice on it. And this is just a schematic showing this part is monolayer, this part is bilayer graphene. Okay? So this was an image from our paper that was highlighted in Asia News in 2009. So by 2007 onwards, we had converted from silicon carbide, looking at all these reconstructions, to graphene. Okay? And strangely, this paper was published in Surface Science, which is a specialized journal in the field. Normally, not many people read it, especially surface scientists, and they're generally not well cited. But we got a certificate. It was a top cited article in 2005 to 2010 for a very specialized topic. And the reason is because people suddenly became interested in graphene. Of course, this was one route to producing graphene. So, sometimes you never know, you understand why people are interested. They're interested from a different perspective. So, you never know, some of your papers they published in the past might become interesting to others. So, graphene, as many of you in this audience probably know, is interesting because of its symmetry to inequivalent carbon atoms in a hexagonal lattice. It has an electronic structure that's different from most materials. In particular, it has what is known as a dispersion relation. This is energy momentum space that is linear. Most cases, it's parabolic. So in other words, the electrons behave as like massless direct fermions. So they behave like photons, massless, except the speed is scaled down by a factor of about 300. So it's interesting to physicists because new phenomena can be studied. But of course, people started looking for applications because the mobility of electrons is very high on the surface. We could make devices. But the only problem is in semiconductor, the way you make devices, you rely on a semiconductor because it will have a band gap. This one has no gap. A semiconductor will have a gap because you need to turn the switch off. That means you want situations where there's no current, and then you need to turn it on, and you can control that by doping and so on. But in this case, there's no band gap, so you can't quite turn your device off. So after the first few years, before people sort of gave up using graphene for electronics, people are using graphene for some aspects of electronics, but not as the active layer now, I believe. But before people gave up on the active layer, they tried ways of opening a band gap in graphene. So these are some of the general ways you can break that symmetry of the carbon atoms by forming a chemical reaction on the surface. So you either put hydrogen, fluorine, or some other molecule, and then you break the sp2 symmetry. It becomes more sp3-like, and hence it opens up a small band gap. That's one way. But the problem is you compromise the mobility of your carriers on the surface. Another way is you reduce the dimensionality, because physicists will tell you that if you reduce the dimensionality of things to a small length scale, then you get quantization of energy effects. So you make a 2D sheet to 1D nanoribbons, you can open a band gap. And another way, okay, it's to use bilayer graphene, apply a perpendicular electric field, create asymmetry between the two layers, and you open a band gap. I'll just say we did explore these two things, okay? So the first chemical reaction, in fact, what Chen Wei did, this was when he was LKY postdoc, since we were working on molecules and surfaces already, right? It was easy for us to do this. He put F40CNQ, a strongly electron withdrawing molecule, on the epitaxial graphene that we were already growing, and it withdrew charge. So this became hole doped, and it also opened a small band gap, okay, but a very small one. And we showed charge transfers through work function changes and so on. So a very simple experiment, the sort that we have been doing all along, just change the substrate. But it turned out to be the first paper of molecular doping of graphene. And because, if anything in scientific field is first, it gets cited quite well. So this Jack's paper is pretty well cited. But of course, dealing with molecules to make devices, ultimately your main problem is stability, right? Because molecules are less stable. We have since then worked on doping with oxides, which are much more stable, but I wouldn't talk about that. But nanoribbons is another thing we explored. So this simulation shows that actually for graphene nanoribbons, it's a bit more complicated. The electronic states depend a lot on its edge structures. So if the edge is zigzag like this, it's always metallic. There's no band gap in this simulation. But if the edge is armchair like this, you can open a band gap at certain widths. Okay? So that's the theory, or the simple theory of it. So we decided to try this, inspired by the work. So we didn't do it first. Klaus Mullen group and Fasel in Germany, Switzerland, they did the bottom-up approach, put this molecule, DBBA, polymerized it, dehydrogenated it, dehydrogenized it, so it became a nanoribbon, right, on the surface, on a catalytic surface. And then it made all these nanoribbons bottom-up by assembling molecules, the chemistry way, which is a good way of doing it perfectly. No lithography needed. Of course, the challenge then is how to transfer all this out. But nevertheless, it was a, in principle, demonstration how you can make very thin nanoribbons, because it has to be very thin before you get a measurable band gap. So we did some work on silver, a different substrate. This is Huang Han again, to assemble this molecule. And this time, because the substrate was a little bit more reactive, we could make nanoribbons of different widths, because they did not just assemble in one direction, they could assemble sideways as well. So if you look at STM, you see different widths in multiples of 7 carbon atoms long, because that's the width of the molecule that you started with. And of course, you can change it by using different molecules and so on. But he graduated, he left, so we didn't carry on this work. I couldn't find a PhD student to carry on this work. But it was interesting because you can see that this is an electronic image. You can see interesting images at the edges. We did some work here by simulating the electronic structures of the image. This was done at low temperature, liquid helium, to get the electronic scattering pattern. So this is not an atomic image. And try to correlate it with theory, which shows that this is Stephen Lewis' group where they did theory and shows that at certain widths you get a band gap as the width gets smaller, but certain widths you don't, either don't or very small band gap. And those widths correspond to this kind of structure we observed. It's actually 2n plus 1. There's a simple formula for the width where you get a no band gap. So that was our foray into nanoribbons. Some people are still working on these nanoribbons. The difficulty is trying to make devices, because it's done bottom-up in vacuum, you have to transfer them or do it in liquid, and then you have to assemble it on substrate and make device like you would make with a carbon nanotube. So it is a challenging, long process. Now, I had another postdoc, an LKY fellow, Da Cheng. Now, he's not a surface scientist. So my group, we do some non-ultra-high vacuum work on the periphery in collaboration with various people. So this work was in collaboration with people like Chong Hao, of course, Chen Wei, and so on, where this time to make the carbon nanoribbon, instead of assembling in a vacuum, why don't we unzip a nanotube? Now, this method of unzipping a single-wall nanotube has been demonstrated before, but this time we unzipped it. You're basically sputtering it with zinc ions with the right momentum. You unzip it because a nanotube has a fixed diameter. It opens up to a fixed width nanoribbon. And if you only unzip it partially through masking or part of it, you get a junction that has a single-wall nanotube, which is metallic in this case, and semiconducting graphene nanoribbon. So you have a metal semiconductor junction, and physicists will know that you can make devices with and photo switches with such junctions here. So we demonstrated that in this paper, which is quite nice. But of course, it's possible to do on single layer, but it's much more challenging to scale up. But again, it was a demonstration of unzipping of nanotubes to make graphene ribbons in part of your circuit. Okay, but I wouldn't elaborate on this because, as I said, it's not the surface science approach, but just to let you know, we do some device work as well. So my third and last story brings me to current, because our graphene story ended probably about 3-4 years ago, because then I guess like funding agencies, they run out of patience with you. After they fund you a certain topic for a certain number of years, they'll say, we funded it already, right? So why should we fund you again? So we're all forced to move to other areas. And of course, the next step is to look at other 2D materials. So my story is about the 2D zoo, because you can actually theoretically think of many other 2D materials besides graphene that you can work on. So let me first of all talk about various 2D materials that people have been exploring. So if people think of 2D carbon, graphene, the next thing they'll think of is 2D silicon, right? Because silicon is so well used. So why can't you make two-dimensional silicon like this? And this is the historical story of some people who made silicene, and the latest is a device that was demonstrated in Asian Nanotechnology in last year. Yeah. So just going down the periodic table, why not? Silicon, it's ubiquitous, we use it in current technology. Except that, actually, you ask a chemist, 2D silicon is not stable, isolated, unlike 2D carbon. So what you see 2D, it's first of all, it's not quite flat. Secondly, it's always on a substrate. So they grow it on silver. So if you look at STM images, this is silver 111. It's grown on silver, okay? But it means, you can't make it stand alone. So obviously the silver does alter the properties a bit. But nevertheless, these people made a device and they published in a high impact journal because they demonstrate silicene transistor. But it is still a great challenge to make real silicene that's isolated, having the theoretical properties that it promises. So So this is a subfield that some people are working on. But of course, periodic table is so big, right? So there are other 2D materials. So the next one, germanium, right? So this is a group that published in Nano Letters recently that claimed to grow 2D germanium, 2D germanium on aluminum. Again, it's done by STM, so it was grown on a substrate, not isolated. So it's a quasi 2D material. So this is 2D germanium. Yeah, so it's still a scientific curiosity of interest. Of course, you can keep going down. Next one is stannine, right? 2D. Again, it's easy to publish in a high-impact journal because you're the first one to demonstrate it. But again, you can see these are just STM. I mean, these are basically the surface science approach. They're just STM images of one layer material on a substrate. In this case, it was I can't remember the substrate. It was a bismuth telluride substrate. So they showed, yes, there's a 2D stannine on it. There are certain properties, but it's not freestanding, so its properties would be altered probably. Yeah. So that's another demonstration. But how about moving to different groups, right? So if I move to group 5, nitrogen will be, I think, hard. But phosphorus, yeah. Now, black phosphorus is a big subfield now. But notice they don't say phosphorine, black phosphorus, because this most well-publicized work by the Fudan group, Yuanpo Zhang's group, it was done by exfoliating black phosphorus, and it's actually several layers, it's multi-layer. Phosphorus is not very stable, it oxidizes easily, but they made a device, it is buckled, theoretically it will be buckled like this, and it had nice transistor characteristics. Some people are pursuing this and think this is a potential way forward. Stability is a major issue. It oxidizes very easily. You need to encapsulate it or do it under controlled conditions. So that's phosphorus. How about the group 3? There's a recent paper in Science on boronine, boron polytypes, borophosphines, okay, by the Northwestern group. So again, they demonstrated growing from a boron source on silver 111. Again, it's on a surface to stabilize it. So they show all these crystals, measured its properties, and as I said, fairly straightforward work, but published in a high-impact journal because they used the story of a new two-dimensional material. Okay, so this is one way of getting published in these journals if you're interested. Okay, but of course, many of these materials, it's going to be a huge challenge to make them useful, but they are interesting anyway. Now, what is perhaps more promising, but there's still many challenges, are to look at compound 2D materials. And many of these layered 2D materials have been well known for a long time. So if they're layered, that means they're stable if you peel them off. And in fact, the Manchester group did demonstrate some of these other compound 2D materials, even with the early graphene paper. It's just that work on them started later. So, for example, these transition metal dichalcogenides are now very popular materials. The reason being, well, there are lots of transition metals to choose from and chalcogens combination. And if you look at the properties, say you look at the band gap, these molybdenum disulfide, tungsten diselenide, they have a band gap that's in a useful range, an optical range, near infrared, and they could be used for devices that could compete with silicon. Okay, black phosphorus is over there. And these are many families of oxides, even oxides that are 2D oxides people are working on. But I shall focus a little bit in the last part of my story on this because we are working on this area now. Okay, so we have decided to work in this area, and hence I have a few students, they're all working on MOS2, tungsten diselenide, and collaborations and so on. So MOS2 as a material has been worked on for a long time. We even use this grease, right? Because it's a layered material, it slides easily, it's a lubricant. And chemists have, if you look at citations by year, there have always been a few hundred papers because it's a catalyst as well. So it's a good catalytic material, so there are a lot of publications on reactions of gases on MOS2 surfaces. People started getting interested in the surface or the 2D structure of it in the 90s, where this is a Biesenbacher group in Denmark that showed a 2D image of several layer thick MOS2 island. okay, in the 90s. But really, it was this paper, I believe it was this paper by EPFL in 2011, where they made a transistor out of single layer MOS2 that caused this sudden increase, okay? And basically with, this is the paper, Andre's case, basically using a single layer MOS2, because it has a band gap, you don't have the problems of graphene where you can't turn it off. You can turn it on and off now. But of course, MOS2 has lower mobility. It is harder to prepare, and there are other issues, growth issues and all that people are still working on. But in principle, you can make a device, 2D device that's very small, using only one layer of material because it has a natural band gap. And this material is interesting. The band gap can be tuned by changing the number of layers. It can transit from a direct to indirect band gap as well. So we started working in this area. So this is the first STM paper we published only last year on MOS2, done by Yuli when she was still a postdoc here. It was basically showing MOS2 single layer on graphite. You can see a periodic, what we call moire pattern, because MOS2 is not lattice matched with graphite. But it doesn't matter in these two-dimensional materials because the interactions are weak. That's why they're called van der Waals heterostructures. They don't bind covalently, so you can actually stack them and not worry about lattice matching. So this is the atomic spacing, confirms the material. We can even measure using spectroscopy, as I mentioned in STM. We can measure the quasi-particle band gap. This is the electronic transport gap, 2.4, which is different from the optical gap because of the what is known as exciton binding energy. So we can get its properties. We can get its properties single, bilayer, tri-layer. You see the steps, and you can see the band gaps are different from single, bilayer, and tri-layer, or the other way around, single, bi, and tri, as predicted by theory. So this was one of the early STM work, so it was interesting. And we also showed that at grain boundaries like this, the band gap, the electronic structure changes. And if we did STM towards the grain boundary and away from grain boundary, it shrinks, and there's some structure at the edge. And it was Kwek Suing's group that helped. This is a different angle. And Yifeng from Suing's group helped do some calculations to show that by having a few % of strain, you can actually change the band gap by that amount. So we believe there's strain at the grain boundary. So you can alter and tune electronic properties through strain. Other people have demonstrated by more deliberate experiments as well. So it's interesting material. You can tune the band gap by straining it by different number of layers. So people are still interested. It's a field of current interest. Tungsten diselenide, another material we're working on. This is a paper that is under revision at Nanolattice, and hopefully it'll be out soon. Again, we see a very nice structure on the surface of single layer. We can measure its band gap. And at grain boundaries here, we see very interesting core structures at these locations. These images are electronic because if you change the bias, they can disappear at certain voltages. That's why I said STM, you are measuring an electronic image. So it's not some molecule on it. It's just the electronic patterns on the surface, as it were, as you change the bias. So we worked out what we believe to be the structure at this location and measured the density of states, the electronic structure at different positions around this location. And again, Suing's group did, and Zhijing did the DFT calculations, look at electron state and match the predicted gap states to the measured gap states. So that's the gist of this paper, which I won't go into too much detail. And of course, the last thing I'll mention, or near the last thing I'll mention, is that because we were working on molecules, we also put molecules on surfaces. This is by Yu Jie, a current PhD student who's here. PTCDA on tungsten diselenide on a substrate graphite. And without going into detail, just showing that this is just tungsten diselenide. This is the molecule that's self-assembled on the surface. We can look at the electronic structure and compare them if we put PTCDA on different substrates and compare why the electronic structure changes and explain through theory, which he's also doing with Suing's supervision, the differences in the electronic structure because of the screening effects, the different screening effects of the different substrates used. This is just a model, the computation that's done. I won't go through this, or I shouldn't have shown all this. Okay, but it basically predicts systematically, with some systematic error, what we observe. Okay. Oh yeah, and I have another PhD student, again, not working on surface science approach, but using tungsten diselenite, putting them on gold templates, plasmonic templates of different sizes, and showing huge photoluminescence on them. So this work done in collaboration with Imperial, SUTD, and also within physics department to show luminescence. So Wang Chua is in Imperial now. She's on the joint PhD program. So we are doing some related device work, in this case plasmonic, to complement our surface science studies. So I'm supposed to finish soon. So these are my final remarks. Yeah, sorry, I rushed a little bit. I think I put in a bit too much. But I'll just say is this editorial I wrote, 3 years ago now, that was the point where people started getting interested in the semiconducting transition metal dichalcogenides, right? And not only that, but they are looking at heterostructures, combining different layers with different materials, making two-dimensional van der Waals heterostructures with very novel properties. So we can not only work on single 2D layers, but we can work on multiple layers of different 2D materials to get properties that we want to make for whatever application we are interested in. So right now, what is the state of art? So this is the Manchester group showing that by stacking these different layers, they can do something like quantum wells that people used to do with gallium arsenide, and make interesting structures with interesting properties. Okay, so these are devices that are being made, 2D van der Waals heterostructures. This is another device using the 2D platform. So this device is a flat device, single layer, but it's entirely made of 2D materials. So graphene is here. Here is used as the contact. The conducting part is graphene. The active part is MOS2, and the dielectric, or the part that isolates the device, is boron nitride. And they're all monolayer. But of course, in this case, I believe they were all stacked manually. So at the moment the device is made, they are all peeled off by Scotch tape and stacked manually. So it's good for physics demonstrations, but a lot more work has to be done if you want to scale them in for industry applications. So the key to industry applications is you have to be able to grow large areas of these materials, and large heterostructures preferably, either vertically stacked or laterally stacked. So this is a science paper from one of our collaborators, Li and Zhong, who actually provides us with some of the materials I showed previously. They had a science paper because they demonstrated the lateral growth of MOS. By the way, this is from KAUST. He's in KAUST now. MOS2 tungsten diselenite junction, not perfectly straight, but reasonably sharp, and demonstrated a device based on that. So this is one area of current interest for growers. They're trying to grow heterostructures either laterally or vertically. This is a review that just got published yesterday that I wrote with our Shenzhen University colleagues. We have a joint center in Shenzhen, so together with some of our PhD students to review these van der Waals 2D materials for optoelectronics. So if you're interested in this field, this is one review. There are many other reviews as well. And I think this is my last slide. So this is from the Graphene Center, one of the promotion slides showing that, broadly speaking, one of the focuses of our own Center for Advanced 2D Materials is to stack many of these interesting materials and look for various applications that could make use of the novel properties that arise because of these stackings. Okay? So we're interested in van der Waals heterostructures, not only inorganic, but for us, we are also interested in the organic-inorganic hybrid structures with molecules, plasmonic, as I showed previously, and so on. So there are many things. The field is still wide open. I don't know how long it will last, but certainly it's interesting now, and hopefully there'll be some applications to keep funding agencies interested. So there are lots of people I have to acknowledge, but I focus mainly on people that whose results I showed. So from our group, current students as well as former students, I mentioned some of them now, many have left. surface science members, our colleagues in physics whom I'm benefited so much in our collaborations, as well as colleagues in other institutions. So I'll end here. Thank you for your attention. And I apologize if I missed out anyone, because actually there are more.
Okay, so thank you to Prof. Wee for the very extensive and then comprehensive work done on the Flatland. Okay, I think you can see that there are many more opportunities to come. As in tradition, the lecture lunchtime lecture series, actually there's no Q&A, but I'm sure many of you may have some questions. So I will call this lecture series to be a close. But if you have questions, I think you can come down and then talk to Prof. Wee about this. So let's join me and thank Professor Andrew Wee for a nice talk again. Yeah. And thank you very much for your for coming to the lectures. Okay, yeah. So those who have questions, you are welcome to come down and ask. Yeah.
Hi, thanks. I saw you coming in.